In R.2, we look at integer exponents and scientific notation. So first, let's talk about algebraic expressions. In algebra, letters such as x and y are known as variables. You can use a variable to represent an unknown quantity. For example, if you earn x dollars per hour and your friend earns $2 more than you per hour, then x plus 2 represents the amount in dollars per hour earned by your friend. When you combine variables and numbers using multiplication, division, addition, and subtraction, as well as powers, you get algebraic expressions. So we are often interested in finding the value of an algebraic expression for a given value of a variable. And this is called evaluating an algebraic expression. So as an example, the number of students in an elementary school is given by 300 plus 20 times x, where x is the number of years since 2013. Evaluate this expression for x equals 4, and then describe what the result means. So the expression 300 plus 20 times x, if x is equal to 4, we're just going to substitute 4 in for x. And so this becomes 300 plus 20 times 4. And this is 300 plus 20 times 4 is 80. And this is 380. So what does this mean? Well, 380 is the number of students at this particular elementary school. And that is going to be the number of students for x equals 4. And remember, x is the number of years since 2013. So if you take 2013 and you add 4 to it, this gives you 2017. So what this means is in the year 2017, there are 380 students at the school. Next, let's define positive integer exponents. So when you have an expression such as this, and we read this as a to the n power, what it means is a multiplied by itself n times. The number a is called the base, and the number n is called the exponent. So just a couple of very quick examples here. If we have 5 to the third power, this means 5 times 5 times 5. Now, if you want to evaluate that, this is equal to 125, but the meaning of the exponent is to multiply 5 by itself 3 times. If you have an expression negative 4 to the third power, this means negative 4 times negative 4 times negative 4. And this would be negative 64. And it's negative because the product of 3 negative numbers is a negative. And finally, if you had something like 2x to the fourth power, this means 2x times 2x times 2x times 2x, which because of commutative and associative properties would be 2 times 2 times 2 times 2 times x times x times x times x. And this is equal to 16x to the fourth power. Now let's discuss negative integer exponents. So if a is a non-zero number and m is a positive integer, then a to the negative m power is defined to be 1 over a to the positive m power. So for example, if we have something like 4 to the negative 2, and we want to write this using positive exponents, by the definition, 4 to the negative 2 is the same as 1 over 4 to the positive 2. Now you can go ahead and evaluate this, and if you did, this would be 1 over 16. Likewise, 1.45 to the negative 3 power is the same as 1 over 1.45 to the third power. Now you can evaluate this, but for this problem you'll probably need a calculator, as 1.45 to the third power is not really easy to do by hand. So if you were to type this into a calculator, you would end up getting 1 over 3.048625. And of course, you could also divide that on a calculator, and that would give you a decimal answer, but I think I'll just leave it in that format. And for the next one, we have x to the negative 4th power divided by y to the 5th power. So to write this without negative exponents, we're going to remember that this is the same as x to the negative 4th power multiplied by 1 over y to the 5th power. All I'm doing there is separating these into two problems, basically. And then x to the negative 4 means 1 over x to the 4th, and then times 1 over y to the 5th. And if we multiply straight across, 1 times 1 is 1, and then x to the 4th times y to the 5th is exactly that. Before we do the next example, let's review properties of integer exponents. And these are all things that I suspect you've learned in the past, but we should probably review them. So if a and b are real numbers, and m and n are integers, then the following properties are true. So a to the m times a to the n is a to the m plus n. So if you have a common base and you're multiplying, you can add the exponents and the base stays the same. If you have a to the m to the n power, you multiply the powers. So that's a to the m times n. ab quantity to the m power, each of the a and the b gets raised to the m power. Next we have a over b quantity to the m power. And here, each of the a and the b gets raised to the m power as well. And then the fifth property is a lot like the first property. If you have a to the m divided by a to the n, once again, we have the same base, so we can subtract the exponents. A to the 1 is a, and anything to the 0 power is 1, as long as you don't have 0 to the 0. And over here to the side, you have an illustration of some examples of these properties. And if you would like, go ahead and pause the video and take a look at those to make sure you understand what each property is saying. Now let's go ahead and look at the next example. So in this example, what we want to do is simplify each expression and write it using positive exponents. So in the first problem here, we have 16x to the 10th power y to the 4th power divided by 4x to the 10th power y to the 8th power. So we can do this without doing what I'm about to show you, but I want to be very specific here. So we can first divide the coefficients, so 16 divided by 4, and then multiply that by x to the 10th divided by x to the 10th, and multiply that by y to the 4th divided by y to the 8th. So I'm kind of grouping these like factors together. 16 divided by 4 is 4. Now, x to the 10 divided by x to the 10, there's a couple of different ways you can do this. One thing you can do is you could just say this is equal to 1, because anything divided by itself is 1. But you can also use the property of subtracting exponents. So if we do that, we would get x to the 10 minus 10. And then for the same reason here, we would get y to the 4 minus 8. Now if we simplify this, we have 4x to the 10 minus 10 is 0, and then y to the 4 minus 8 is negative 4. And then this is 4 times x to the 0 is 1, because anything to the 0 is 1. And then y to the negative 4 is 1 over y to the positive 4. And so in the end here, we can put 1s underneath these. And if you multiply straight across, you get 4 over y to the 4th. Now, I don't think that you really need to do this step. I was just basically showing you that you could do that step. I think it's much better back here if you just realize that anything divided by itself is 1. So in fact, in the very beginning here, we could have just canceled those out, right? In the next example, we have the quantity 3x to the negative 2 to the 3rd power divided by x to the negative 5. Now, there's a couple of different ways to approach this. I'm going to take a very direct approach. So in the numerator, what I have is the product of two things here, and then that is raised to the third power. So this power 3 gets applied to each one of these. That's a property of exponents. So we have 3 to the third power, and then we have x to the negative 2 to the third power. And then in the bottom, we still have x to the negative 5. Now, if we do the math on this, 3 to the third power is 27. X to the negative 2 to the 3 is x to the negative 6. So all we're doing here is multiplying these powers together. And then in the denominator, we have x to the negative 5. And now, because these have the same base, we can subtract these exponents. So we end up getting 27 times x to the negative 6 minus negative 5. And that is 27x to the negative 6 plus 5, which is 27x to the negative 1. And then finally, x to the negative 1 is the same as 1 over x to the positive 1. And this ends up being 27 over x. So the main thing is you just want to kind of take it slow. Don't go too fast. If you go fast, sometimes you make mistakes. And for the last example here, we have 54s squared t to the negative 3 over 6zt quantity to the negative 2. All right. So first thing I'm going to do is inside the parentheses, I'm going to simplify as much as I can. So one thing I can do here is I can take 54 and divide it by 6. If I do that, I get 9. And that will be in the numerator. And then I have an s squared, and I have a z in the bottom, and I have a t in the bottom. And then the other thing I'm going to do is I'm going to take this t to the negative 3, and I'm just going to drop it down to the bottom and make it t to the positive 3. And I can do that because of definitions of negative exponents. Now, the negative exponent on the outside, I'm going to leave that alone. I don't want to do anything with that at this time. Now, just to simplify a little bit here, what we have is 9s squared over zt to the 4th. And it's the 4th because this t right here is a first power, so I'm just adding 1 plus 3 here to get 4. And now that whole thing is raised to the negative 2. Now, when you have a negative exponent like this, a fraction to a negative power, what you can do is just flip the fraction. So literally I take zt to the 4, put it on top, 9s squared goes to the bottom, and when I do that, this negative 2 becomes a positive 2. And now I just need to raise everything inside the parentheses to the positive 2 power. So we have z squared, we have t to the 4th squared, we have 9 squared, and finally s squared squared. And if we do all this, we get z squared t to the 8 divided by 81s to the 4th. So again, when dealing with expressions where we use properties of exponents, you just need to take things slow enough so that we don't make any silly mistakes. Next, we will talk briefly about scientific notation. Scientific notation is just a more convenient way to write very large or very small numbers. And the way we do it is we express the number by taking a number a and multiplying it by a power of 10. Now the number a has to be in between 1 and 10, not including 10. And the number b here is an integer exponent. Okay? Now the best way to understand scientific notation is to just do some examples. So to express each of the following numbers here in scientific notation, what we're going to do is we're first going to take the raw number that we have. So in this case, we have 328.5. And we're going to move that decimal to the place where that number now becomes a number in between 1 and 10. To do that, we need to put the decimal right after the 3 here, right? So 328.5 is going to become 3.285. So what I had to do this is I had to take this decimal and move it 2 places to the left. So if I want 3.285 to be equal to the number that we started with, I need to move that decimal 2 places to the right. So we're going to multiply by 10 to the second power. And the reason for that is because when you do this, 10 to the second power is 100. And when you multiply by 100, that just amounts to moving the decimal place 2 places to the right. So literally, the power of 10 just tells you how to move the decimal. So if it's a positive number, you're going to move it that many spaces to the right. And if it's a negative number, you'll move it that many spaces to the left. Let's take a look at the second number, 4.69. In scientific notation, 4.69, well, notice that the decimal point is already in a spot where this number is between 1 and 10. So we don't actually need to move the decimal at all. So in this case, when you put it in scientific notation, you're going to multiply by 10 to the 0 because you don't need to move the decimal at all. The next number, 0.00712. This is not a number between 1 and 10. So if I want to make this a number between 1 and 10, I need to move this decimal here so that we get 7.12. Now, when I do my scientific notation, I have to multiply by 10 to the negative 3 power because to get the number back to where we started, I need to move this decimal 3 places to the left. Finally, we have negative 435.6. Again, I need to make that number between 1 and 10. Now, when you have a negative number like this, just simply ignore the negative sign. So we're going to focus on 435.6. We're going to turn that into 4.356 to make it a number in between 1 and 10. And then we will remember that it was negative. And then I'm going to multiply by 10 to whatever power is going to move that decimal back to where it used to be. Well, it used to be here. So to move that decimal here, I need to move it 2 places to the right. Converting from scientific notation to decimal form is actually a little bit easier. So you can go ahead and read the procedure here for doing that, but it's basically the same as what I just outlined a minute ago. So let's take a look at these examples. We have 2.1 times 10 to the 5th power. This tells us to take the number 2.1 and move the decimal 5 places to the right. So if I take 2.1 and I start moving the decimal 1, 2, 3, 4, 5, when you move it 5 places to the right, if there are no numbers there, you have to fill those in with zeros. So this literally becomes 210,000, which is 210,000. In the second part, we have 3.47 times 10 to the negative 3. Now, what this is telling you to do is take this decimal and move it 3 places to the left because it's a negative exponent. So if I take 3.47 and I move the decimal 1, 2, 3 places to the left, again, I have to fill this in with zeros. And because I'm moving it to the left and there's nothing there, I'm going to put the decimal right there. And so this becomes the number 0.00347. So another way to think about scientific notation is that when your power is positive, that generally represents a large number. And when your power is negative, this generally represents a small number. One final example with scientific notation. In 2012, Japan had a population of 1.27 times 10 to the 8th power. and a land area of 3.64 times 10 to the 5th square kilometers, what is the population density of Japan? That is, the number of people per square kilometer of land. Express your answer in scientific notation. So what we're going to do is simply take the number of people divided by the number of square kilometers. Well, the number of people is 1.27 times 10 to the 8th power, and the number of square kilometers is 3.64 times 10 to the 5th power. So when we do this, we're going to break it down into two parts. We have 1.27 divided by 3.64 times 10 to the 8th divided by 10 to the 5th. So we're going to do the math here. 1.27 divided by 3.64. You can use a calculator to do that part. And if you do that, you get 0.3489011. And then for the second part, we have 10 to the 8th divided by 10 to the 5th. To do this, we use properties of exponents, and that's going to be 10 to the 8 minus 5, which is 10 to the 3rd power. Now, this number is not quite in scientific notation. And another thing is, notice that in the beginning, we only had 3 significant digits here. So we're going to go ahead and round this to 3 significant digits. So what I have here is 0.3489. That becomes 0.349 times 10 to the 3rd. Now, the reason this is not in scientific notation is because this number is not between 1 and 10. So again, to make it between 1 and 10, we need to move that decimal here. So that becomes 3.49 times, and then what happens to the power of 10? Well, again, think about what we just did. We moved it one place to the right. So really, it should go back one place to the left to be what it used to be. So we had 10 to the 3rd, but we moved it one place to the right, so we need to move it one place to the left to get back the number that we used to have. And so this is 3.49 times 10 squared. And what I'm doing there is I'm simply adding these exponents together. 3 plus -1 is 2. And that's our answer. So how many people are there per square mile? Per square kilometer in Japan? 3.49 times 10 squared. Now, 3.49 times 10 squared is 349. So there are 349 people per square kilometer in Japan. That's pretty dense.